So Robert is going to talk about a specific example where real intent was used to do some clock domain crossing verification.
Okay, so thank you very much, especially to all who allowed me to swap. We had to swap because of getting a flight. I'm Robert Eichner. I'm the FAE for the Field Application Engineer for Real Intent here in Europe. By the way, we also use Verdi for debugging in the flow. What I wanted to talk now about is how a combination of CDC or how formal verification can add to CDC traditional structural verification to find additional problems you wouldn't have found otherwise to make the design more robust, more stable. So I go from introduction to a case study we did on a specific small handshake design. So some statistics, we did a survey at Daxis here, 300 participants, people who showed up at our booth, stating that more than half are starting new design within 3 months, means design cycles have shrunk. Then the number of clock domains, about 1/3 had more than 50 clock domains in their design, and clock domain crossings, sorry. And with CDCs, we always mean asynchronous CDCs. We're not talking about synchronous CDCs. Then we asked how many customers had a bug, a late ECO because of a problem in the CDC, and that was more than 2/3 or about 2/3 of them. And the last question was what are they going to invest in for the next tool choice? What do they want to add to their flow? And CDC analysis and verification was on top of it, followed by automated formal verification. That's just as an intro. The general problem, I think you're all aware of it, is the metastability problem. If you have an asynchronous clock domain crossing, if the data and the clock show up at the same time, you might end up in some kind of time where the receiving flop swings. This swing propagates as some, let's say, unknown then through the design. You have to capture it up front, and if you have an asynchronous clock domain crossing, you will always somewhere get those because you never know when data and clock shows up exactly. So this is not a problem for synchronous clock domain crossings where you have well-defined and aligned edges and you know your timing and you can verify this. Synchronous clock domain crossings with traditional SDA, but for asynchronous clock domain crossings you need some kind of add-on or additional analysis. So in the previous case you could simply add another flip-flop after the first receiving flop to overcome the time until the flop swings in. The more advanced way of coping with those CDCs is an example design here is a handshake-based or protocol-based approach where you synchronize the control signal. The laser is not very. So where you're synchronizing the control signal with these two flops, you have edge detection, you have a control logic, and you control the data path. This is a multi-cycle path. This is control signal. And what you can, so the control crossing you see here, that must be synchronized. If this is a bus, only one signal should have a transition at the same time. So there should be a gray encoding on this address bus then. It should be free of hazards and glitches, and it should be stable for more than one receiving clock cycle. So this is interesting if your transmit flop runs at a higher frequency than your receiving flop, of course. Otherwise, you don't have a problem with with the width of this control signal at this point. The other thing you have to take care of is the data crossing needs to be a multi-cycle path. So what the structural analysis determines or finds out is whether you have these two flip-flop stages here and whether you have these data paths controlled here, right? So what you can find out with the structural analysis really is if this is a true multi-cycle path where the data shouldn't be captured with the first edge of the receiving clock, but with the second edge to avoid any kind of, let's say, crap coming in here being captured. And these two in green, these two you can cover with formal analysis included or integrated into the CDC checking tool. There are two other things you can find out, by the way. This is like if you have a glitch here, this can be found using formal techniques, like if synthesis merges the MUX with the XOR, which sometimes happens if you forget to put a don't touch on it. What it also can find out is if this is a bus, that the control signal is really gray encoded. So some terminology. First, the pulse width check, as I said, that determines whether the pulse width of the control signal is larger than the receiving clock cycle. Then the data stability, that this is a true multi-cycle path, that the capturing happens at the second edge of the receiving clock after the data has changed. And the transmit and receive frequencies. Then how is it traditionally done? How is it done today? So most do not use, or most customers I have do not use a dedicated CDC analysis tool. They use some scripts built around SDA. They try to do this with a gate level simulation environment, moving edges to provoke the metastability and see what happens with the design. I have some who just have some kind of mechanism to identify these places, these CDCs, and then they say, okay, we do a visual check of the whole thing, and if the designer says it works, it's going to work. Or these protocols, or this protocol design I showed you just before, is checked just using RTL simulation. That leads to that in many cases these CDC checking happens after the implementation, where implementation, I call it synthesis. So you're working on the net list, so it's done by the verification teams, it's done by the backend teams. So if a problem is detected, finally that leads to a longer iteration cycle because they have to go back to the designer to change the design and run through the implementation cycle again, and before that, of course, through all the RTL regressions they might have. So it's a fix late in the flow, and as always, fixing something later in the flow is more expensive in any term. So what we recommend is move to a dedicated CDC validation tool, verification tool, and also automate the verification of the CDCs, as there's always there's this paradigm or this rule that the front-end designer shouldn't verify his own block with his own parameters and test bench, right? By automating that, you can move the verification of the CDC to the front end and get a more error-free or more robust design in the back end. Now, looking at the variables or how this is implemented, this is the same picture than before. So you have a control logic and you have a detector controlling the data path in this handshake example. So the option for the control logic is having that counter-based, having it finite state machine-based or a pulse stretcher. For the detector, you can have a signal transition detection like the XOR you've seen before, or you can have a finite state machine. The variables, of course, is the clock frequencies from transmit, receive domain, and also how these edges are aligned, the ratios of them, and also, of course, the reset timing. Many people do not take the reset timing into account. When is the reset released, and to which clock, synchronized to which clock is it released? Are they all released at the same time or at different times? In many cases, there's a reset generator sequence, there's a reset sequence, and you have to take that into account for the clock domain crossings as well, of course. Now what we did is we took this design you just saw, we used for the control logic a counter-based approach for the detector, this low to high transition with an XOR, and the resets in that case are aligned, are ideal. The pulse width results is pretty straightforward in that case. So the higher the ratio between the transmitting and receiving clock, the higher the counter value has to be. Of course, the counter value determines the throughput of your clock domain crossing, right? The higher the ratio, the higher you have to count. This is nothing unexpected. Now, if it comes to looking at the same thing, looking at the data stability checks with formal verification, you find out that you have like a counter of 4 which passes, and then you have a few which do not pass, and then you have passing values again. Thank you. So if you might think that if you find out that 4 is sufficient and you change something in your ratio, or if you increase the counter because your clock ratios are changing, you can just assume that it works. In that case, it doesn't actually. So if you go up with the ratios, you see that this is not symmetric. This is not really linear, which counter values pass and which do not. Now, looking at this failing case, for instance, and this is a waveform generated by the formal tool, you see that in this case, data stability fails. You have the control signal going up after half of the counter value. Then you see 2 edges later of the receiving clock. You see the max control going up. Data changes when the counter wraps, and then it's taken over by the next edge of the receiving clock, which is a failure. For the value of 15, it worked in this sample. We cannot reproduce, or we do not produce good cases yet, so this is on the list of enhancements. But you will see the other failing case for a value of 16. Again, the data changes and it's taken over by the next rising edge of the receiving clock. Stressing that a bit now by if the resets are offset, right? This is wrong here, so they are not aligned. So if the resets are offset, you see that all of a sudden the pulse width is no longer linear or straightforward as well. So what that means is you cannot make you cannot take this based on assumptions. You take a pretty high risk in getting an unstable design as soon as reset scheme changes, as soon as the ratios of the clock changes, as soon as the offset of the clocks change. So for the verification engineers, it saves test bench development times, and they do not need a deep understanding of the design. For the cut guys, it saves the backend CDC verification time and the effort. For the design engineers, they can really explore their design and see whether it's stable, robust, whether it has a good quality or not, what they hand off to the verification team. So, as I said, you need dedicated CDC tools to really find out those issues. If you automate these things, you can move this to the front-end guys, to the designers, and it enhances productivity that way, and it removes risk. for it.
Okay, thank you.
Thank you very much.
Is there any questions from the audience? CDC, one question for me. So this is something where the verification can be pushed back to the design team rather than necessarily have it done by the verification engineer.
Well, the real idea of it is that it allows that the design team can do this verification in an earlier stage. Of course, we also have customers who are looking into the formal approach where the verification team says they see a problem, the designer says there isn't, and the verification team then uses this formal approach to prove that it doesn't work when they go back to the designer. So we have this approach, of course, as well. So, but it works in the front end and in the back end. It works on RTL, it works on netlist.
Okay.
Yeah.
Okay, thank you. Any more? Okay, thank you very much, Robert.
Thank you.